So this is the structure of the old IBM 36091 machine. This is called the Tomasulo machine, named after the person who invented the algorithm. So it has the instruction queue. The instruction fetch is happening here, and it's going to be put in this queue. There are 6 instructions that can go into the queue at a time. There are these floating point registers. So mainly this algorithm was used on floating point operations because they have variable latency, and they also have a longer latency as compared to other instructions. Then there are these reservation stations here. I'll describe that later on. So you have 2 sets of reservation stations, one for the adders and one for the multipliers, and both of them are floating point adders and multipliers. Then this whole thing is a memory unit, which we have not discussed so far and we will discuss later. So basically we have the load buffer and the store buffer, both of them going into the memory unit, and the address unit connecting to both of these buffers. Now we are going to mainly demonstrate how the reservation station is used and what is this common data bus. So basically this is the data bus that is going to take the output from these execution units and then send the result to the reservation station and to the register. So we will discuss the working of this. So let us consider these set of instructions here, and we will now use this Tomasulo machine to describe how these instructions are executed in an out of order fashion. So we will use the stages called as fetch, decode, execute, and write back to understand this. And we are assuming that at the end of the execute stage, what happens is that the execution units put the data onto what is called the common data bus. The results are put onto the common data bus. So if the multiplier and the adder complete at the same time, they're going to have different data buses here. It's shown as a single bus, but of course there are 2 buses which connect to the adder and the multiplier, and the result is put out onto the data bus. So that is the assumption. The assumption is that after execute, the data bus or the CDB, the common data bus, gets the result. By write back, we mean register write back. So basically from the CDB, the results are written back to the registers as well as to the reservation station. So we'll see why it's written to the reservation station and so on. Now, if our assumptions change, our pipeline diagram is going to change. So we are going to now demonstrate how to write a pipeline diagram to demonstrate out of order execution. So based on these assumptions, I'm going to show how this pipeline diagram will work. Now, the actual algorithm used in the machine was basically issue, execute, and write back. But we have introduced a stage called decode stage here so that we can demonstrate the working of this reservation station better. Now let us assume also that the add takes 3 cycles. So remember that we are only demonstrating multiply and addition here. We have not demonstrated load stores. We will discuss this later. So the add has 3 cycle latency and the multiply takes 5 cycles to execute. We are assuming 1 adder and 1 multiplier in this design. So with these assumptions, let us see how to write the pipeline diagram.
We're now going to describe how this set of instructions go through the pipeline. So firstly, let me describe the contents of this slide. So firstly, we have the register allocation table, which we're going to use for register renaming. This contains the register name. Then you have the valid tag here, which is going to indicate whether the value that is present here is valid or not valid. Then we have the tag. I'll describe the tag later on. This is the value of the register in the register allocation table. Now, these are the set of reservation stations. These are for add and these are for mul. So we are assuming there are 4 sets of reservation stations for add and 4 for mul. So this again depends on the architecture of the machine. There is a set of reservation stations for the add unit, and these are for the multiply unit, and these are the 2 functional units we are assuming. This also carries the tag. Again, the tag is the same as this tag here, and I'll describe that later. Then this is the value that is computed by the functional unit. Now the contents of the reservation station or the RS is, again, it has a valid bit. Then we have the tag. This is basically the rename tag. I'll describe this in the next slide. Then we have the value of the operand. So basically the reservation station is going to contain 2 sources. For example, if the multiply instruction has 2 sources, R1 and R2, those 2 are going to go in here. I'll describe the function of this in the next slide. So the valid tag and the value holds good for source 1 and source 2. Similarly, for the multiply also there is source 1 and source 2. So this is cycle 0. So before we start the fetch of the instruction. Now let us move to cycle 1. The first instruction is being fetched, the multiply. This is the fetch stage, cycle 1. Nothing else happens here in the first cycle because the instruction has just been fetched. And we are only doing single issue per cycle. So we are fetching only one instruction per cycle. And therefore, this is the only instruction that is being fetched in cycle 1. Cycle 2, the instruction is decoded. We mentioned that there are 4 phases: instruction fetch, decode, execute, and write back. So we'll follow these 4 phases for this example. So what happens in the decode stage is the instruction is decoded. It is figured out that it is a mul instruction, that it has 2 sources R1 and R2, and it has a destination R3. So along with the decode of the instruction, the other steps in this cycle are: the machine allocates a reservation station entry for the multiply. This is happening in the decode stage, and it first basically checks if the reservation station for mul is free. So since we do not have any other instructions before this, it checks if there is any free reservation station, and it puts this instruction into this reservation station. Now the reservation station has a name here, so we have been given the name E here. That is the name of the first reservation station. So like I said, the source 1 and source 2 are going to get into the reservation station. Now the next thing it does is it checks for the source operand values, so R1 and R2. So that is the whole goal of the reservation station. It wants to see if the sources are available. If the sources are available, it is going to go to the execution unit. If the source operands are not available, it is going to wait in the reservation station. So this is our basic assumption. So now it checks for the sources. Now how to check for the sources? It checks for those sources in the register allocation table. So now R1 and R2 are the sources. They are both valid and their values are 1 and 2. So those are now updated in the reservation station. The source operand R1, whose value is 1, has been read from the RAT and then updated here. Similarly, R2 has been updated here. And both of those are now valid because both of them are available and both their operands are ready. Now the next thing to do is to rename the destination. So the destination rename also happens in this same stage. So firstly, we decoded the instruction. Secondly, we have read the source operands and allocated an RS entry. And the third step is to do a destination rename. So the destination for mul is R3 and it will be renamed to the name of the reservation station. The reservation station is E, and this is the new name for this register, which is R3. And now it has been marked as invalid because R3 is yet to be computed by this multiply functional unit, and therefore it is now being marked as invalid and its value will not be used by any future instruction. Now these are the steps for the multiply. For the next instruction add, we just do the fetch in the cycle 2. Now in cycle 3, the easiest thing to do is fetch the third instruction, so that is a fetch. Now what is happening with multiply is that it checks if the 2 source operands are valid. If they are valid, and therefore it will be sent to the execution unit for execution. Therefore the execution stage has started. Since it has 5 cycles of latency, it is going to now take E1, E2, E3, etc. to complete its execution. Now while the execution is going on, the next instruction, the instruction 2, is now going to go into its decode stage, which means that we are going to repeat all of the steps that we did for the previous instruction. The first thing is to find if any reservation station is free for its sources. Now R3 and R4, this is an add instruction, therefore it will go into the first reservation station. It will now check for R3 and R4. Now where is it going to check for R3, R4? It is going to check for it in the register allocation table. Now R3 is found to be invalid, which means that it is waiting on some previous instruction. So the first source here, R3, is not going to have a valid tag because it is still waiting for a previous instruction to finish. Its tag is going to be now updated here, which means that there is a connection between this source R3 to the multiply reservation station here. I hope you can see the connection here. And its value is not updated because it is not computed. The source 2 is R4. Now R4 is again checked in the RAT. It has a valid value here. This should have been 1 here. And the valid value is now updated in the reservation station. So now what happens here is that the add has been decoded, but it cannot continue with execution because one of its sources is invalid. And Although the multiply reservation station has passed on the instruction to the multiply unit, we cannot free up this reservation station. So do not free up the reservation station for mul till the write back is complete, because we are carrying this name of this reservation station. So if you free this up and then put some other instruction here, we are going to lose that connection that we have right now, and therefore we are not going to free up this reservation station for multiply, although we have passed on the instruction to the multiply unit. So towards the end of this whole phase, we will understand why this is done like this. Now the last thing that happens here with the second instruction is R5 has been renamed to the name of the reservation station which carries the operands, that is A, and it has been marked as invalid. So these are the steps in the cycle 3. Now in cycle 4, again the multiply continues with its execution. This is the second cycle of execution. It is going to take 5 cycles to complete. Meanwhile, the add cannot continue, because although now you can look at the reason why it cannot continue, but the way it is actually done in hardware is that it looks up for R3 and the R3 is not available because it is now waiting for the E reservation station to complete its operation. So this has to stall or wait. But then now you can see the out of order execution from the next cycle onwards. Now the third add has been decoded now, and then the fourth add has been now fetched. So in the previous cycle we had fetched the third add, and now we are decoding the third add, and I'm not going to repeat the steps. We repeat the same steps as we did for the previous instruction. We look up for the sources R2 and R6 in the RAT if they are valid. They are valid, so we allocate a reservation station if it is free. We update the values of the sources, that is 2 and 6, and then we rename the destination, that is R7, to the name of the reservation station that carries the sources, that is R7 has been now renamed. Now R2 and R6 are not waiting on any other previous instruction, so in the next cycle they are good to go to the execution unit. The fourth add has been fetched. Now in cycle 5, you'll see that the first mul is continuing with execution, the second add is waiting. The third add in the meantime has gone ahead from the reservation station to the execution unit, because it doesn't have to wait for any previous instruction to finish. Now this is the first step where you will see the out of order execution happening actually in hardware. And like I said previously, we will not be freeing up this reservation station till the write back happens. Now add will take another 3 cycles to complete. In the meantime, the next add has been decoded, so we follow the same steps. R10 has been renamed, that is the destination. It has been allocated a reservation station, and then the multiply has been now fetched. The next cycle, the same steps continue. The first one continues, the first 3 actually continue with execution. The fourth add is continuing its execution. Actually, the second one is stalled. The rest of them are actually executing. Now the fifth instruction, which is the multiply, has been decoded. Now here it is going to be allocated a reservation station. We're going to look up for the operands R7 and R10, and we find that both of them are invalid, which means they are waiting on some previous instruction to finish. So that's what we write here. It has a tag, which means it is actually the rename tag of the reservation station. So now in all of this, you see that the rename has been done with respect to a reservation station name and not with respect to some other register. And now this instruction cannot now continue with its execution because it is still waiting, and both of its source operands are invalid. And then the last instruction has now been fetched. Now in the next cycle, the multiply is finishing its execution, and like we assumed, it is going to write the result to the CDB in the same cycle. The add is also completing its execution, and therefore that's also going to write its result to the CDB. Now the second instruction, add, cannot start execution right now because the result has not yet come to the registers or to the reservation station, so it has to wait one more cycle. This add is continuing with its execution. This mul is waiting for previous ones to finish, and the last add is interesting actually because it is of course going to be given a reservation station and all that, but then R5 is going to be renamed. R5 has already been renamed previously, if you observe here, to the name of A, and now it is going to be renamed again to the new reservation station name, which is D. So that is what is happening in cycle 7. At this point, all instructions have been decoded and renamed, so no more renaming is going to happen for these set of instructions. So cycle 8 is when a lot of important observations have to be made here. So we're going to break this cycle up into multiple slides because there are multiple instructions finishing operation, and we also want to explain why the CDB is connected to the RAT and why is it connected to the RS and so on. So let us first look at the multiply completing its write back. So what happens in write back is, in the previous cycle, the instruction has completed and returned the result to the CDB. That is called as broadcast. The value, the result has been broadcasted. The result is basically 1 multiplied by 2 and the result is 2. And that is going to carry the same tag as its reservation station. So E is the reservation station which had issued the MUL, and the result is also going to carry the same name, and that is the reason we are not freeing up this reservation station yet. Now the result is going to go to the RAT and to the RS. So it is not going to go directly to the registers. It is called register write back, but it is first going to the RAT and to the RS. So the RAT and the RS are going to do what is called as a tag match and check if any of their registers were renamed with the tag E and if they had a valid bit equals 0. So if the RAT had a tag E and if its valid is 0, what this means was this was a destination of this instruction and it was renamed to the reservation station name E, and it is waiting for the value from the functional unit. So if I just move to the next slide here, so here we can see that the R3 has now been updated to the value from the functional unit, which was E equals 2, and then now it is changed to valid equals 1. So that is the change happening in the RAT. And in the meantime, the CDB also sends the result to the reservation stations. We'll see that why it is done. But then what this does is, again, you compare the tag. So when it compares the tag for this source, it knows that this instruction, whose destination has been renamed to A, was waiting for the source operand, which was actually dependent on E functional unit. So essentially this means that this add instruction was waiting for the MUL to complete. Now instead of reading this value from the register R3, what the CDB is doing or helping out is that it is directly giving us that value by connecting the CDB to the reservation station. So what happens in that cycle is that, I've just shown it in the next slide, is that this value is getting captured in the reservation station directly as the value of the source, and you update the valid bit so that the next cycle onwards, this can get issued to the functional unit and it can carry on with its execution. So you don't have to wait for the register R3 to get its value and then update the value here and then send it to the execution unit. So this is the advantage of connecting the CDB to the reservation station. So these are the changes that are happening here in this particular cycle. Of course, it means that there are a large number of bus interconnections. So now I'll move to this next slide, wherein we have updated the value of E to 2 in all the units, that is in the RAT as well as in the RS. So the add, which was waiting in the RS, can now start its execution in the next cycle. Now the third add in the meantime has also completed its execution and it is now issuing the result onto the CDB. I'm again describing the same cycle. I've just split it up into 8A and 8B so that we can describe this easily. So now similar steps happen for the B reservation station also. You match the tag in the RAT and you also match the tag in the reservation station and update its value. So in the same cycle, it is going to get updated and then the valid is also going to get updated. Now what we can do is we can free up the E and the B reservation stations because we are done using these names. So no other places in the architecture have the name E and B at the sources or at the destination. So now you can free the reservation station and therefore these have been now freed. So in the meantime, in this cycle, the fourth instruction has also completed its execution. It is in its stage, E3 stage, and its value is going to get returned to the CDB. So these are the changes happening in this cycle 8, and I'm going to describe the next cycle onwards in the next slide.